Hello everyone, welcome to the problem session from elective potential. This is problem number 32 from your reference book Halliday, Resnick, Walker. So in this problem it said that a non-uniform linear charge density distribution of a rod. So that means the charge is not uniformly distributed, it's a non-uniform distribution, or you can say the non-linear distribution. And that distribution is given by, say that charge density is lambda, which would be as a function of x, but b is a constant. So that means with the increasing length, your charge density will be basically increased, right? So that equation says that one. So that's why we write down. And this rod, say we consider that the rod has a length actually that L. The length of the rod is L, and it situated at a axis starting from x equal to 0 to, say this is x equal to 0.2. So that's mean the length of the rod basically the 0.2 meter. Now we have to find out, they asked to find out that electric potential at the 2 point, at the origin at that point, and another point say at a distance, say y equal to where this y actually 0.15 meter. Fine, at these 2 points we have to find out that electric potential. Fine, to solve this one, basically what we are going to do, the idea is basically initially we choose a differential element of this rod, right? Say in this segment the charge of this rod, differential charge is del q, and the length of this differential element, say the dx, and the distance from say that here to here, say that x. Now we can find out that the potential for this differential element at the origin, we can write, say that dv would be k into dq divided by x, right? This is the definition for the potential for the point charge we can use over here. Now this dq we can find out because we define the linear charge density over here, non-linear charge density, whatever, say this is actually dq over dx, right? It's not equal to total charge divided by total length. It should be different because it's a non-linear distribution. So that's why we can write that dq would be lambda into dx, while lambda actually that bx into dx. So now if we want to find out that total electric potential at the origin by the total rod, we are going to integrate this one, right? So we'll write down the total V would be basically integration of 0 to L. So that's mean which is the length of this rod would be dV, right? So we can write, so this V would be, say that we have to integrate from 0 to length of this rod actually that 0.2, and dv actually the k into dq we write down actually that lambda into dx divided by x, or the lambda we can replace by that quantity bx, right? Is a constant, or b is a constant basically. 0.2 k lambda is bx into dx divided by x. Now this x will be the cancel out, then k and b basically the constant, so we can factor out this quantity. So it will be the k into b integration of 0.2 into dx. If you integrate, you will find out only that x, right? So this would be that x, so 0 to 0.2, right? then we can find out, if you plug in that value, is going to v would be k into b into 0.2, right? 0.2 minus 0. So we'll find out basically. Now I'm going to plug in. So k is Coulomb constant, which is 9 into 10 to the power 9. B is a constant which is given. The B is 20 nanocoulomb per meter square. So I'll write down this would be 20 into 10 to the power minus 9 into 0.2. So if you do that, then you will find out that potential at the origin due to that rod would be 36 volt. So this is actually the answer number 1, right? The answer number A. Now in the question B, they ask you what is the potential at point Y, where Y is equal to 0.5 meter from the Y axis. So fine, to find out that one, what we are going to do, we'll consider this is Y. At that point, we'll find out the potential. Then we have to find out that distance from here to here. What is that differential element distance? So I'm choosing that distance, basically that R. If it is the distance is R, then we can write the potential at the point Y. We will write for differential potential at point Y equal to 0.15 meter. We can write, say, dV would be k dq over r, where r we can replace dq, we can replace lambda into dx, and r could be replaced basically root over x square plus y square, right? So you can find out from the figure. So this is actually your x, that distance. From here we assume that that distance is basically that x, which we write down over here, and this is actually y. Then x square plus y square would be that r square. So fine. Now for total potential, we are going to integrate that rod. So this v would be integration from 0 to L into dV, right? So I'm going to plug in, so 0 to 0.2, and dV actually k, lambda basically that bx, right? I'm into dx divided by root over x square plus y square. Now since k and b basically that constant, we can factor out. So k and b, so this is 0 to 0.2 x into dx divided by x square plus y square, where y is constant, right? X is variable over here. Now this is a differential form, or it's a integration formula. You probably know that. If you have, I'm writing that if this is the known formula, if I say the integration in a formula, say x into dx root over x square plus minus, I'm writing the general formula, plus minus a square, then that integration would be basically root over x square plus minus a square, right? If x square plus a square, your answer will be root over x square plus a square. If x square minus a square, your answer will be root over x square minus a square. Using that formula, we can write our solution for the potential. It would be kb, right? It would be root over x square plus y square, limiting value is 0 to 0.2, right? So now you can write this formula would be kb, so Once you plug in that y x equal to the 0, you'll find out only the y. So I'm plugging that one. So I'll write, say, x is 0.2 square plus y is 0.15 square, right? Square root minus x is 0, right? The second limit 0 plus 0.15 square. I'm just plugging the value of y, which is 0.15. Then if you solve this one, you'll find out, you see, square, you'll find out that potential at the y-axis at a distance 0.15 would be basically 18 volt. So this is the answer number, question number B. Okay, thank you very much.